Modern virtual worlds report tens of millions of daily active users, yet the actual interactive spaces they provide remain severely restricted. Looking at the concurrent user hard caps on major platforms reveals the extent of the problem. A densely populated Roblox instance maxes out around 700 concurrent users. Fortnite caps its Battle Royale mode at 100, while Minecraft servers become functionally unstable past 400 players. In standard web architecture, scaling is straightforward. You add centralized servers to handle the traffic. However, real-time 3D environments require a level of continuous synchronization that this centralized model cannot support. The primary hurdle to metaverse scale lies in distributed systems architecture, well beyond the reach of standard graphics rendering. The barrier to scaling virtual worlds is a mathematical limit inherent to any interactive simulation, the O of n squared interaction problem. This node graph shows how O of n squared scaling behaves in a physics engine. Every single object or player added to a shared simulation exponentially increases the number of potential collision and interaction equations the server must calculate per frame. Standard, stateless web requests operate in parallel, scaling linearly. A physics engine, however, requires intensive, continuous state synchronization between every node. Breaking this mathematical barrier requires the platform to distribute the simulation load itself across the network. Legacy attempts to distribute server load rely on geography. Engineers slice the 3D virtual world into a spatial grid, assigning different servers to handle specific 3D tiles. This 3D grid shows why spatial partitioning fails. When a train crosses a grid boundary, simulating its parts on distinct servers triggers massive communication overhead. Instead, min-cut data flow partitioning treats the world as a graph, grouping dependent objects into physics islands to minimize network cuts. Scaling a dynamic world requires a network architecture that partitions based on actual computational dependency rather than virtual geography. Even with perfect partitioning, distributed networks are bound by the speed of light. A standard 110 millisecond ping between Tokyo and London inherently breaks a 60 frame per second real-time rendering loop. Multiplayer games hide latency using dead reckoning, but as the vehicle stutters and snaps back into place, the prediction fails, forcing a visual correction. Dead reckoning falls apart when faced with complex user-generated scripting logic. A simple algorithm cannot linearly extrapolate the outcome of a script, triggering an unpredictable chain reaction. The metaverse alternative is client-side authoritative speculation. In this model, the local client device runs a complete replica of the simulation tile locally. It rolls forward the state to current virtual time, predicting logical outcomes, scripts, variables, and physics before the server confirms them. Scaling these experiences transforms the client device into an active compute node, moving beyond the role of a passive video receiver. For edge clients to run these massive speculative simulations locally without stalling, the platform's scripting engine must execute with near-zero overhead. This diagram shows the internal division of labor. The heavy computational physics are written in optimized C++, separated entirely from the high-level game logic. That logic is driven by user-generated scripts, written in Lua, which interface with the physics backend. The performance bottleneck occurs where these two environments meet. Standard Lua requires an expensive index hash table lookup every single time a script attempts to trigger a C++ engine event. This Lua memory stack representation shows the optimization. By introducing a bespoke XX name call meta method, the system bypasses the expensive XX index table lookup entirely. XX name call places the instance and method name directly onto the stack, allowing for a single direct invocation into the C++ environment. Macro-level network scaling is entirely dependent on these micro-level compiler optimizations. Without XX name call, distributed client nodes would choke on their own logic. This visualization maps the global infrastructure required to coordinate tens of millions of speculative nodes. We must look past the local client VM and examine the global mesh. Engineers at this scale have to manage the thundering herd. This is a catastrophic network event where over 1 million concurrent users attempt to establish UDP connections to a single experience simultaneously, following a major update. Standard public cloud infrastructure, like AWS or Google Cloud, is economically and architecturally unsuited for this specific density of stateful, real-time UDP traffic. The latency requirements are too strict, and the bandwidth costs are too high. This topology chart details the bespoke solution, a private cloud of over 135,000 servers. Massive UDP spikes hit edge centers, are filtered by Envoy proxies, and route into Linux containers. Using eBPF, the system achieves kernel-level observability, monitoring connection states without routing latency. By offloading the physics simulation to optimized client nodes, the central private cloud is freed to focus purely on state reconciliation and load balancing. True scale requires an integrated engineering stack. It requires restructuring physics to bypass the ON-square bottleneck, rewriting Lua VN Mite code for C++ interoperability, and deploying a bespoke 135,000 server private cloud. Engineers must manage 3D simulations with the same logic applied to distributed databases to reach these scale targets. In this model, the virtual world is a series of materialized views. The clients rely on speculative view maintenance, and the servers rely on min-cut data partitioning to keep those views synchronized across the network. Realizing the metaverse depends on mastering the distributed systems architecture needed to defeat the physical limits of network latency.